Welcome to lesson 87. Starting in this lesson, we're going to look at something called Maclaurin polynomial and Maclaurin series and how they relate to functions that are known as transcendental functions. So you can take some time to read the paragraph here by pausing the video, or the key takeaway from this paragraph is to keep curious about certain questions, like have you ever wondered how calculators give you the values of sine, cosine, cotangent of any angle, or the square root, or the nth root of any positive numbers, or how your calculators calculate log of any positive numbers that you may have. It turns out that calculators don't memorize every single function. They don't really have a big table for these functions. Instead, in the eyes of calculators, these functions are polynomials. So they use polynomial approximations, and depending on how accurate, how many decimal places you need your numbers to be, then they're going to make use of up to a certain number of terms in the polynomials to help you calculate the answers. So we're going to learn how this type of approximation works in the next couple of lessons. So I'm going to begin by talking a little bit about linear approximation. If you consider this random function in blue on the graph shown here, and the red line here indicates the tangent line of this function at a certain point, x0, comma, f of x0. Right now, I know that, the whole function here is a curve. What if I keep zooming in to a really small portion of this function? Then we cannot deny the fact that within a very small region, okay? This function has a segment that kind of looks exactly, or almost exactly, like the tangent here is just like a straight line. So this is what we mean by linear approximation of a curve, right? So because we're looking at a very small section of a curve and treat it almost like a straight line, because we know that a linear relation is very easy to work with, okay? So let's see how this works out. So we say that we can assume that the function f of x is differentiable at the point x0, and then the tangent line drawn at this point can closely approximate the function for the values of any x values near x0. Since the equation of a tangent is linear, I'm going to use point slope form. Okay, to write out the equation of the tangent. So we have y minus the y value at the point, so f of x0, equal to the slope of the tangent, and we know that it is f prime x0 multiplied by x minus x0, right? We have used this before. If I rearrange this equation to isolate for y, then if I want to use a line to approximate this particular section of the function, then I can say that the polynomial can be written as y equals to f prime of x0 times x minus x0, the original right side of the linear equation, plus f of x0. Okay, so what we know about this particular approximation is that it's linear, and also f prime matches the gradient of the function. Okay, and we're talking about a very small section. So here is the key. It's the values of x that are close to x0, okay, the point of interest here. Now we know that as we continue to move away from the location of x0, let's say I'm here now, okay, at a new position of x, let's call it xa. can I say that the red line that we see, the tangent that we see on the graph, is a good approximation of the region near XA? Of course not, because near this region, I have to use a linear approximation where we know for sure that the slope of that line is negative, right? So this only works within a close proximity, okay, of a point that you pick. But then, what else can we do to improve this approximation? Okay, I want to use a simpler function, a polynomial, to represent a certain section of a function. Well, what if instead of using lines, we use curves, right? That's going to improve how closely my approximated version of the function is going to look like the real thing. And if I use higher derivatives, what about that? So by using the first derivative, we're matching the gradient. Say if I use a second derivative, now we can also use that to match concavity, right? So let me write this down. And also we can use a higher derivative. So for example, if I use the second derivative, then we can match concavity as well. Okay. You are now going to work on investigation 10. You will try to come up with a polynomial p of x of degree 5, okay, to approximate the function f of x equals to ln 1 plus x. Make sure when you're doing number 2, you do not simplify the fractions that you get. And then in part 3, you're going to try to come up with a general rule based on what you see in number 2. And then in number 4, you will actually write out a polynomial, p of x, using the coefficients that you find. And then in number 5 and 6, you can compare the polynomial function that you come up with to the function of f of x equals to ln 1 plus x. Okay, so you can pause the video now and then resume it when you're done. How did you do in investigation 10? This is what I worked out. So I first worked out f prime of x and p prime of x up to the 5th derivatives. And then I let each derivative at 0 equal each other to solve for the coefficients a1 to a5. I also noticed that the denominators of each one of these coefficients of an is basically factorials, right? Because if you go back to your work in taking the derivatives, you're basically multiplying, say, in the second derivative, like 3 times 2, 4 times 3, 5 times 4 to get 6, 12, and 20 in those terms. So you actually have a bunch of factorials here, which looks like, let me go to the next page, the general expression for each coefficient a sub n can be represented by the nth derivative of f at 0 divided by the n factorial. When I simplify those coefficients, I get the polynomial p of x in number 4 listed here. And the critical part here is number 5. I think it really takes us home here. After I graph both f of x in blue and p of x in red, notice how there is a certain region very close to x equals to 0 where we're evaluating our first derivatives at. These two graphs actually overlap each other, okay? But as we move away from x equals to 0, you can tell that, well, obviously f of x no longer matches or can no longer be used to approximate the function, can no longer be used to approximate the function f of x. And that's the whole idea of a function approximation here. Okay. So the key concept that we would like to learn from this investigation is summarized in number 6, where we say a finite number of terms of an infinite series can be used to approximate a function in a local region. So the key here is local region. And of course, if I make p of x my polynomial to have a higher degree into an infinite series like plus dot 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 here, if I keep doing that, the more accurate, okay, my result is going to be. Okay. The particular type of function approximation that we're interested in is known as the Maclaurin polynomial. And to generate the Maclaurin polynomial of degree n, we can make use of the formula shown in the box here. The polynomial p of x starts from x to the power of 0 term, x squared term, x cubed term, all the way to the x to the power of n term, giving it n degrees. And then the coefficients come from a progression where we have f of 0. And then the second coefficient will be f prime of 0 over 1 factorial. And then for the x squared term, we have f double prime of 0 over 2 factorial. So the number of, well, the nth derivative and the nth factorial matches with the degree of x in this polynomial. Or you can write a general form using sigma notation. And when we say we have a Maclaurin polynomial, we're dealing with a finite sum. So in the summation, there is an endpoint, meaning that there are only up to n terms, okay? As a side note, a Maclaurin polynomial approximates a function always near x equals to 0, near the origin. It belongs to a bigger family of polynomials known as the Taylor polynomials that some of you may encounter in your university studies. So let's take a look at the first example. Here, we're going to find the Maclaurin polynomial of degree 0, 1, 2, and 3, and n for e to the power of x. Ignore the graph on the side for now. We'll be looking at that a little later. In order to construct the nth derivative of the Maclaurin series, we can start by writing out f of x, which is e to the x, f prime of x, same thing, f second derivative, third derivative, and then so on up to the nth derivative of e to the power of x, which is still itself. So we have picked a very simple function as our first example. We actually need the value of these derivatives when evaluated at x equals to 0. So f of 0 is 1, f prime of 0 is 1. They are all 1s here in this case. Right, e to the power of 0 is 1. Dot, dot, dot. F of n, 0, 1. Okay, so there we go. So what does the degree n Maclaurin polynomial look like? It's going to look like the following. P of x equal to, starting from 0, ending at 0, f and the kth derivative of f at 0 over k factorial x to the power of k, which gives me, at the top here, we found that all the derivatives, including f of 0, is 1. So 1 over 0 factorial x to the power of 0, which is 1. Okay? And then degree 1 polynomial, p of x. We have, starting from k equals to 0, 1, the general formula, f of 0, k derivative over k factorial x to the k. So first term is 1 plus, if k is 1, I have the first derivative at 0, which is 1, over 1 factorial x to the power of 1. So this is 1 plus x, okay? Continuing like that, degree 2 Maclaurin polynomial, the sigma would be the same going from that. Okay, so I'm not going to write that part. I know that the first two terms will resemble what we already have. And then the third term is going to be the second derivative at 0, 1 over 2 factorial x squared. Okay, and then degree 3, pretty much the same thing, but now we're adding on 1 plus x squared over 2 plus, this time third derivative at 0 is 1, 3 factorial x cubed, just like that. So this simplifies to 1 plus x squared over 2 plus x cubed over 3 times 2 times 1, 6. Okay, and then the general polynomial, it's going to be up to the nth term of this whole thing. And so you can write it as the sigma of k from 0 to n, while all of those derivative at 0 is equal to 1 in this case. So I can simplify that as 1 over k factorial times x to the power of k. This gives you a finite sum that approximates the function that we have, which is y equals to e to the power of x. So now let's revisit this graph here. What this graph is that it actually shows the different degree Maclaurin polynomial for the function f of e to the power of x. So this is the line, right? The line is degree 1 approximation. The blue part, of course, this is the degree 0 of p of x. And then you can tell that we actually have a parabola. I think it's the purple one. This is your degree 2 approximation. And then the black line is the degree 3 approximation, because the red one, I'm very sure, the red part here is y equals to e to the power of x squared. So this one here. So look how the approximation actually improves as we go from degree 0, which seriously look nothing like the red line, right? Near 0, x equal to 0. How about the straight line? Well, if I really magnified my graph here, maybe a little portion of the green function will overlap with the red function. So there is my linear approximation. And then does it improve when I go to the purple, the quadratic? I think so, right? Because now the curve now starts matching. And then I can see that the black function here, the degree 3 function, is the best approximation to the curve of y equals to e to the power of x amongst the 4 different variations that we have. So it does improve by increasing the degree of the function. And again, it's very important to emphasize that because this is a local approximation, we're really just focusing on the area very close to x equals to 0, okay? Anywhere outside of that region, we know that these polynomial functions will not be a good approximation to the function y equals to e to the power of x. Okay, so here, let's take a look at Maclaurin series. So when we compare the Maclaurin series to a Maclaurin polynomial, the main difference is that the polynomial gives you an approximation of a function using a polynomial near the region x equals to 0. But when we want to represent the exact function of, say, sine x, cos x, e to the power of x, and so on and so forth, to improve the accuracy of the approximation, we now turn to an infinite series known as the Maclaurin series. So if you take a look at in the yellow box here we have the formula for finding the Maclaurin series. You will notice that it is actually very, very similar to what we have used to generate the Maclaurin polynomial, right? You start from f of 0 plus f prime of 0 over 1 factorial times x plus f double prime at 0 over 2 factorial times x to the power of 2. So again, the nth derivative, n factorial, matches with the degree n of the term. The only difference really here is that instead of stopping at the nth degree term, we're going to continue to infinitely many terms. And if you notice at the top of the sigma notation, you can see that we are replacing n with the infinity symbol. In this course, when we deal with Maclaurin series, we will assume that as n approaches infinity, the sum of these n terms will tend toward a limit. In other words, the series converges. Okay? And any test for convergence is beyond the scope of this course. You will worry about that in your university studies. And we say that for any values of x where the infinite series converges, it gives you the exact representation of a function. Okay? So now let's take a look at example 2, where we're going to find the Maclaurin series for sine x. Make sure you refer to that formula shown in the box on the page. I'm just going to use my formula booklet here. We know that in order to find the Maclaurin series of sine, I need to evaluate f of 0, f prime of 0, f double prime. Like I need a pattern. Okay, I need to generate a pattern. So let's start with that. So f of x is sine x. F prime of x is cos x. F double prime of x is negative sine x. F triple prime of x is negative cos x. And I know that f to the, not power, but the fourth derivative of f of x is going to be negative of negative sine x, which is sine x. So it's really going in a cycle, right? There is a pattern here. And then I need the values of f of 0. Sine 0 is 0. F prime of 0, cos 0 is 1. F double prime of 0, negative 0 is 0. F triple prime of 0, negative cosine 0 is negative 1. And then we're back to the fourth derivative at 0. We're back to sine x again, so that will be 0. Okay, so it looks like we're alternating between 0, 1, 0, negative 1, 0, 1, 0, negative 1, like that. In this particular Maclaurin series for x, like these are the coefficients, right? This or part of the coefficients. So let's try to write this out. Sine x is equal to, first term is 0. Second term is plus f prime of 0 over 1 factorial x to the power of 1 plus f double prime at 0, so that whole thing is 0, plus f triple prime of 0, so negative 1. This is my x cubed term, so this is going to be 3 factorial plus 0. Let's try another one. So we know we alternate between positive 1, negative 1. So the next one is 1 over, this is going to be 5. So 5 factorial, and don't forget, and Maclaurin series is infinite. We need the dot 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 at the end. And now let's try to generalize this whole series. So here we have the sigma of n from 0 to infinity to indicate an infinite series. And then the first term is 1 over 1 factorial x. And then the second term is negative 1 over 3 factorial x cubed. So we know that we are alternating in the numerator, positive and negative 1. So we can use powers of negative 1. And then the denominator is odd numbers factorial. So I have 2n plus 1 factorial. And then x to the power of 1, 3, 5. So these are also odd numbers. So here we match up with the odd numbers that we see in the denominator. Okay. Example 3. So what have we got here? Here we are asked to find the Maclaurin series for x times sine x. Now don't reinvent the wheel. We already found out what the Maclaurin series for sine x is. Okay, that's from example 2. So here we can modify that sigma notation by multiplying x in front of this sigma notation. So negative 1 to the power of n, 2n plus 1 factorial x to the power of 2n plus 1. Using exponent laws, here I'm multiplying x to the power of 1 to x to the power of 2n plus 1. That allows me to combine the x's as the following. So here I have x to the power of 2n plus 1, which is plus 2. So let's list the first couple of terms of this new Maclaurin series. First term, when x is equal to 0, I have 1 over 2 times 0 over plus 1 factorial, so that's 1. X to the power of 0 plus 2, that's x squared, okay? Second term, when n is equal to 1, I have negative 1 to the power of 1, so that's negative 1. 2 plus 1 is 3. 3 factorial is 6. And then x to the power of 2 times 1, 2 plus 2, 4. When x is equal to 2, I have positive 1 over 4 plus 1 is 5. 5 factorial is 120. X to the power of 3 times 2, no, 0, 1, 2. 2 times 2 plus 2, 6. Okay, and then plus dot, dot, dot. Part B. Here we are looking for the Maclaurin series for sine of 2x. So again, this is a sine function. So I just need to modify what I substitute, because now this is a composite function with 2x instead of x. So in this case here, I'm running out of room, so let me redo it here. Sine of 2x is then the sine Maclaurin series. Wherever we don't have x involved, there will be no change. But then, instead of substituting x, we substitute 2x, and then to the power of 2n plus 1. Okay, so we can work out a few terms here. Okay, first coefficient, 0. So it's 1 over 1 is 1. I have 2x to the power of 2 times 0, 0 plus 1 is 1. That's it. Minus 1 over 6. And then here I have 2x to the power of 2 plus 1, 3. And then plus 1 over 120. And then 2x to the power of 2 times 2 plus 1, 5. Okay, let's clean up. 2x minus 8 over 6, or it's 4 over 3, x cubed. This is 32 over 120. We can simplify that by 8, which is 4 over 15, x to the power of 5. One thing I did not include on the last line, but I shouldn't miss, is the dot, dot, dot. You can use minus, you can use plus. It's okay because you're just alternating after, okay? And that's your first lesson on Maclaurin polynomial and Maclaurin series.